Hello everyone. In this module, we are going to learn about igneous rocks, and the very first thing that we're going to discuss about is why do rocks melt? So here are the lesson goals for this video. You should be able to differentiate magma and lava, as well as describe processes involved in generating magma by the end of this video. So a couple of things that I would like to mention here. Igneous rocks are actually the most common rock type on Earth because all the mantle and most of the oceanic crust, plus most of the continental crust, it is mostly made of igneous rocks. Okay, and whenever you think about igneous rocks, you can think about volcanoes. We have magma right here and then lava. So volcanic activity or magmatic activity is definitely something that you could imagine when we think about igneous rocks. And the reason for that is because the formation of igneous rocks involve the freezing or solidification of magma and lava. Okay, and this is something that we already learned from last module, but I would like to remind you about the main difference between these two terms. Both refer to molten rocks or liquid rocks, but the main difference is simply magma is molten rocks that are still below the ground, whereas lava, it is actually molten rocks that already reaches the surface of the earth. Okay, so again, magma still below the ground, lava is already above the ground. So another thing that you need to remember is that the mantle of the earth is actually pretty solid. The asthenosphere and the entire mantle is actually pretty solid. So where does the magma come from? How does Mother Nature generate melts? Okay, so that is the big question right here, and that's something that we'd like to address in this video. There are actually three main ways to melt rocks. The first one is through a process called heat transfer melting, simply by applying high temperature, and it's pretty straightforward. Okay, by applying high temperature, you got some melts. The second one is by lowering the pressure, and that process is called decompression melting. And the third one is by adding water or other types of volatiles. And we're going to learn about what volatiles are. Okay, so adding water into the hot rocks could also could also help the rocks to melt. So let's take a look at the first method, which is heat transfer melting. This typically occurs in the crustal rocks when you have hot magma rising and pools right below the crustal rocks right here. Now, what's going to happen is that these hot magma will start to generate some heat, and it will cause the overlying crustal rocks to melt. Okay, so very simple. Hot stuff will melt the colder stuff, right? And these crustal rocks, when it starts to melt, it would generate some new magma right here, and it may create some new magma chamber, and that magma chamber will create some volcanic activity on the surface of the earth. Okay, so that is the first process, which is called heat transfer melting. And the second process is called decompression melting. And this is a bit counterintuitive, so I want to take this a bit slowly. So here's the thing. Here on the left, you see a cross section of the Earth that shows the Earth's geothermal gradient, meaning that here, by looking at this cross section, we can figure out what temperature, how hot the Earth is as we go deeper into the Earth. Okay, so for example, at 100 kilometer right below our feet, okay, it turns out that temperature reaches about 1,000 degrees Celsius. And if we go further to 200 kilometer below the surface, the temperature would be about, I don't know, maybe 1,300 degrees Celsius right there. Okay, so the interesting fact is that if we measure the temperature of this lava right here at erupting volcanoes, it's actually only about 1,000 degrees Celsius. much less than 1300 degrees Celsius. Yet, this mantle stuff is all solid, not liquid. Okay? So here, 1000 degrees Celsius, we already got molten rocks on the surface, but here at 1300 degrees Celsius, we still have some solid mantle. Why? And the answer for that is pressure. Okay, so it turns out that the melting temperature of the earth, I'm sorry, melting temperature of the rocks is actually a function of both pressure and temperature. And that is the two things that I want you to think about and remember. Okay, pressure and temperature are the two main factors that contribute to the melting temperature of rocks. Okay. So here's a graph of decompression melting. So again, here's a graph that would help us to understand decompression melting. Let's take a look at this graph, and let's take a look at these two lines here. These red lines indicate that everything on the right side of it is totally liquid. Okay, whereas this green line right here, everything on the left side of that green line will be totally solid. Okay, so this is the solidest line and this is the liquidest line. Okay, and it goes down simply because it follows the depth of the earth. And as we go deeper into the deeper part of the earth, then the pressure will also keep increasing. Okay, so that's the basic concept of this graph. Now another thing that I would like to mention here is that as we go deeper, as I mentioned earlier, that the pressure of the earth will increase, and the greater the confining pressure, the higher the melting temperature. Okay, so that simply means that one way to melt the rocks in the mantle is by reducing the confining pressure. Okay, and that process again is called decompression melting. So for example, here I have rock A, and rock A sits at about 300 kilometer below the surface. Okay, and if you read the temperature will be about, I don't know, maybe 1800 maybe, or 1700 or so. Okay, so our goal is to melt this rock A without changing the temperature. Now, in order to do that is one way to do that is simply by bringing these rocks towards the surface of the earth. Okay, so let's take a look at that. So here we're gonna take these rocks all the way up to a shallower depth, and what we're gonna do here, stop at point B right there. Okay, right at that solidus line. Now the same rock is now at about maybe 180 kilometer below the surface. Okay, from about 300 kilometer below the surface. Now by bringing these rocks towards the surface of the earth, what we just did is simply lowering the pressure. Okay, from 100,000 bars to about 50,000 bars. Now, because we already hit this green line, then these rocks again will start to melt. Okay, now if we bringing the rocks even further towards the shallower part of the earth, then again it will just start to melt even more. Okay, so that is what we call, that is the process, what we call as, that is called as decompression melting. And decompression melting is very common in various settings. Basically, the first one is it is very common in a mantle plume. Here we have hot rising rocks that are from the core mantle boundary. Here we have the depth right here, and if you bring these rocks all the way to the surface near the lithospheric mantle right here, then again it will start to experience the drop in pressure. As a as a result, then we will start to have some melts. Not only that, if we have continental rifting, okay, so the thinning of the continental lithosphere causes the pressure right underneath the rift to drop. And again, as a consequence, it will start to generate some magma, okay, because of the lowering of the pressure beneath the thin continental lithosphere. And do not forget about decompression melting beneath a mid-ocean ridge, okay? Here we have two plates that are moving apart. So therefore, it actually releases a lot of pressure right underneath the ridge, and it will allow the underlying mantle to start to melt because of the lowering pressure. And again, that is the reason why we have volcanic activity along mid-ocean ridge. And the third process is by adding some volatiles, and the process is called flux melting. Okay, volatiles are gas or liquid at temperatures and pressures on the Earth's surface, and one of the two of the most common examples would be H2O and CO2. And we know that H2O on Earth's surface is mostly liquid, right, or water, and CO2 on Earth's surface is mostly in gas phase. Okay, so again, these are good examples of volatiles, and these two are also very common in mantle rocks. And the reason why volatiles is important in this process is because they actually help break bonds at crystal surface. So again, for example, here I have two curves now. One is for dry basalt, the dry melting curve for basalt, and here is the wet melting curve for basalt. So the same rock type, the main difference here is that one, we have dry basalt, and here this is for wet basalt. Okay, if I have the same sample, same basalt, that is dry versus wet basalt, look at this. For dry basalt, I would need high temperature at about maybe 1200 degrees Celsius. But for the same rock type, with added volatiles in it, and in this case water, it will tend to lower the temperature, to lower the melting temperature to about, I don't know, maybe 700 or 600 degrees Celsius. Okay? So there are significant difference between these two scenarios, and the reason for that is simply because we have added water into the basalt here. Okay, so adding volatiles will tend to lower the temperature at which rocks will melt. And this process is very common in convergent plate boundaries where we have subduction zones. The subducting plate right here, the downgoing plate, actually brings a lot of water, a lot of minerals that are rich in water. And as you go deeper into the mantle, that water will be squeezed out because of the pressure, right? And then that water will start to go out and into the hot asthenosphere right over here. And that is the reason why we will start to generate magma in subduction zone. And that is the reason why we always have volcanic activity right in front of subduction zone. Okay, so I think that is all that I would like to mention here, but there are three questions that I would like to ask you for this video. The first one is, which is the correct statement about magma or lava? The second question is, which three processes cause rocks to melt? And the third questions is which process will not cause rocks to melt? All right. If you do have questions, as usual, let me know, and I'll see you again in the next sub module. Bye bye now.